Hi friends, so welcome to this session and here we'll be discussing about another search algorithm which is by the name jump search. So here in the jump search algorithm, this is also a bit similar to the binary search algorithm wherein it expects a sorted array to be available to it, and also it relies on the divide and conquer strategy. So the thing about jump search is that let's say we have a sorted array of 5 elements 1, 2, 3, 4 and 5, and the index positions, as we know in Python, it is 0 index, so 0 1 2 3 and 4. All right, so these are the indexes of this particular array. And how does this algorithm works out? It again, since it is working on the divide and conquer strategy, so it looks out to basically reduce the problem space at every iteration. So the problem space, how does it takes into consideration? So let's say we are into the first iteration, and let's assume it is sorted in the ascending fashion. So we have the start variable which is initialized to 0. We have a value which is jump size, which is considered in this particular jump search algorithm. And normally, or the best value that we have is the square root of the size of the array and int of it. So basically the array here is 5, so under root of 5, and then taking int of it will be coming down to somewhere around 2. Like under 5 is 2.232, and then the int of it is 2. So we have the jump size as 2, and then what we do is we take up the end is equal to the start plus the jump size. So that becomes, the start is 0 right now and the jump size is 2, so it becomes the value 2. So what it does is every time it will be breaking down into these problem spaces and then basically running the linear search within that problem space. So these are the three things which are available: start, the jump size, and the end at the at the start of every iteration. So now what happens is, let's take an example here. So we have this particular sorted array. Now let's say we have, let's take an example 10, 20, 30, 40, 50, 60 and 70. And we have the indexes. Yes, we have the indexes 0, 1, 2, 3, 4, 5 and 6. And now what we need to find out, let's say we need to find out the value 60, whether it is available in this particular array or not. So that is a value 60 which we are going to search. So we have here the array and the value. So this is the value and this is the array x, right? So now what we will do in the first iteration, we will have the values of start as 0. Then we have the jump size. Jump size is what for this particular array? It is it is consisting of the 7 elements. The length of it is 7. So under root of 7 and then the int of it. So basically it would be somewhere around 2 itself, right? Or yeah, it will be int of it will be coming around 2 itself. The square of 3 is 9 and square of 2 is 4. So between 2 and 3 the value would be there and the int of it will be 2. So now we will have the end as 2. So now for this first problem space, we have broken down this particular iteration between 0, 1 and 2. These three elements. This is the first problem space for the first iteration. Now what it does is it basically takes up the value which is to be searched, which is 60, and compares it with the value which is available in the array at the end index, and which is x of 2 is equal to, and this is this particular index which is the value 30. So now 60 is basically greater than 30. So it does so, it keeps on getting into the problem spaces or jumping across the problem spaces till it finds a end value of the array which is greater than the value to be searched, right? So it will do it in an iterative fashion on working out or looking out for a problem space that has the end element greater than the given value, since it is sorted in the ascending order. So now what it does is, so in the first iteration it sees out that the end value is 30 and which is less than 60, so it will now jump it to the second iteration. So now what the problem space it will define is the start will become equals to the end, and the earlier value of end was 2. Again, now the end will become the value which is the current value of start, that is 2, plus the jump size. Jump size is also 2. So end will become, now let's change the mark color here. So the start is 2. Here the start is 2 and it will go till 4 here, right? Um, Now here there could be certain other ways of optimization as well, like you can basically make the value of the start as end plus 1, so it might have started with 3 rather than starting with 2 because two values overlap, right? In the first problem space also we got 2, in the second space problem space also we are getting 2, so there are certain other optimizations that could also be there on top of it. But majorly the algorithm is, or the intention of the algorithm is this, that it keeps on jumping the problem spaces as per the jump size till it gets a value, the end value of that problem space to be greater than the value that is to be searched. So now we have got end is equal to 4 and the value of x of end, that is x of 4, is equal to 50. So now 50, how does it compare to 60? Still 50 is less than 60, right? So it will go into the third iteration. So let me change the color here. So it will go into the third iteration, wherein what it will do is it will have the start value. Start will be the previous end value. The previous end value was 4. The end value now will be the current start value plus the jump size, which is 2 is equal to 6. So the problem space is now coming from start is equal to 4 till end is equal to 6. Now what is the x element or the end element of this particular problem space? X of n, that is x of 6, that is at the index 6. This is the sixth position and it has the value 70. Now 70 is greater than 60, which is a value which we need to search. So now our problem space has basically been given as this, wherein we have the elements from 50, 60 and 70. That is, the star is equal to 4. That is this particular problem space. Star is equal to 4 and is equal to 6. So this is now problem space given to us, and herein we just need to apply the linear search, which is basically comparing each of these elements for equality with the value to be found. So what jump search has done basically is, jump search is somewhere between the binary search and the linear search in case of efficiency, and the time complexity is O under root n for the jump search. So what it has done is basically, before applying the linear search, it is a basically a modification of the linear search to make it more efficient. Before applying the linear search, which traverses to each of these elements to find out the value to be searched or the target value to be searched, it breaks, first of all, aims at basically reducing the problem space for the linear search to take in. So this is the basic concept of the jump search. And now let's see how we can implement it into the particular code. And we'll also look at the related algorithm flowchart. So this is what we discussed about the jump search. So jump search also follows a divide and conquer methodology. it actually does a linear search when finding the matching value within the problem space defined by the jump. That is what we saw. And the prerequisite for this is also same as that of the binary search, that the collection on which this particular value needs to be found out, that needs to be in the sorted order. So coming further here, so this is the flowchart for this particular algorithm. So we start and then we have the input values as the list X that we have in the sorted order, and then the value val that we need to search in that particular list. Then we take the length of the list. We have the problem space start counter as the 0th index, and we have the jump size calculated for the optimal purpose. The jump size is always taken to be the under root of n being the length of the array, and the end is equal to the jump size for the initial value. So if the jump size is 2, as was the in the example that we saw, so we will have the end is equal to 2 and the start is equal to 0th element. So here as we discussed about the jump search, so jump search also follows a divide and conquer strategy, and basically it actually is a linear search when finding the matching value within the problem space defined by the jump. So it is essentially the modification over the jump search, wherein it basically reduces the problem space at every iteration, and then within that problem space, it basically executes a linear search. The prerequisite is again the same as that of the binary search, that okay, the collection needs to be in the ascending or the descending order. That is, it needs to be an assorted, it needs to be an assorted fashion. And now what we do is we basically try to understand this algorithm that we have seen working in the previous in the session on the note. So herein we start with the value of the array X and the value val, and then we compute the length of the list. We have the start pointer as the initial value as 0. The jump size, the most optimal value of the jump size is under root of n being the length of the array, and the end of the problem space for the first iteration is the jump size itself. So we have at the initial level the values of start as 0 and the value of end as the jump size, which in the previous example that we took was 2. Now we do this particular iteration of going into each of the problem spaces, and we do it till we get start, or we do it while we have the value of the start less than n minus 1. And please have execute a caution over here that do not equate it to n minus 1, otherwise it will go into the infinite loop for some of the use cases. The intuition being, if we are at the last problem space, so the last problem space would have the end value is equal to n minus 1, which is the last index. Now, in the next iteration, what would happen is we would equate the value of end to start, right? So now the start value would be equal to n minus 1, the last execution. So at that point in time, we did not to execute the loop because there is no value which would be existing for the elements greater than the last index. So now we what we do is we basically iterate it till we have gone into all the problem spaces. Now if we have a value which, if we find out the for one of the problem space the end element is greater than equal to the value which is to be searched, then we basically select that problem space, and in that problem space we do a linear search. Now if as a result of the linear search, well, if we find out the value, then it is returned as value is found. And at the end of the linear search, if we do not find that particular value, then it is returned as not found. Because if it does not exist in this particular problem space, it does not exist in any other problem space as well. So but we'll be exiting the entire execution, and we will be mentioning that okay, the value did not exist in this particular list. If we are basically iterating through the problem spaces and the end element of that problem space is not greater than equal to the value which is to be found, then we basically go into the next problem space. And how do we define the coordinates of the problem space? The next problem space, we define the start coordinate as the value of the end coordinate of the previous problem space, and the end coordinate of that particular problem space would be the value of start plus the jump size, given that value of start plus jump size is not excessive or is not exceeding the value of n minus 1. So that is a check we basically make in the code. So now let's look at the implementation of it. So herein the jump search algorithm is implemented in Python. So we define the function jump search implementation. We pass it in this x and the value val which needs to be searched. We initialize the values. N is equal to the length of the sorted list that we have. We have the jump size, which is the square root of the length of the list, and we have the initial start counter as 0, and the end counter is equal to jump size for the first problem space. Now we set initialize the value of have found is equal to false, and now we have while loop which we have taken over here, wherein we check for the condition of exit, which is if start is less than n minus 1, then we need to basically go on executing. If start comes equals to n minus 1, then signal that we need to exit the processing, and the value is not to be found in the entire list, or the problem space itself was not able to be uh, found out. So now here we have, and these print statements are just for demonstration purposes, would be helpful for understanding. Now we check if the val is less than or equal to x of n, or in other words, if the x of n, that is the end coordinate of the problem space, if it has an element which is greater than or equal to the value, then that is the problem space we need to enter into. So then if this condition is satisfied, then we basically enter into that particular problem space, and then we execute the linear search into it. Now there are current a couple of optimizations we could also place in here in this linear search execution, wherein if we have the value, so we are basically going through each of the elements of that problem space. Here I have implemented it taking it in the reverse order, that is I start with the end and basically end at the start minus 1, so that all the elements are covered in that problem space, and I take a step size of -1. Um, let's see. So in this particular execution, what happens is if it is equal to if the x value or the end coordinate of the problem space would have been equal to the value, then we would have straight away found it in the first iteration itself in the linear search while searching linearly in that particular problem space. So that is why I take it from the end. It just depends on the intuition, which intuition you better want to follow. It could as well be the case that okay, the value is will be located at the start rather than the end of that particular problem space. So it just depends. You want to implement it from back to the from the back or from the start. I prefer it this way. Now, if the value is equal to x of I, so then we say okay, we have found the element. And here is this particular optimization for the linear search. Now, if the value becomes greater than x of I, that is, we are traversing linearly in that particular list. And now we knew that, okay, end element is greater than the value that we are finding. And we are now traversing. And now if we are traversing and we come to a stage where we find that, okay, the element of the array or value has now grown in, its value is now greater than the current element that we are comparing against, then that's the signal that okay, we need to exit this particular search, because the value would not be existing in this particular problem space, and because it is sorted in an ascending fashion, and we are going in from back to the start. And now the value which we started with, which was the end element of the problem space, was greater than the value. Now the current element of the problem space has become less than the value. So then that means that okay, the equated value which is to be searched in the problem space, which is a sorted problem space, does not exist, and we can basically exit that execution. So we say that okay, have found is equal to false in that particular problem space, and we break out of it, and we again break out of the bigger while loop as well, because we had entered into that selected problem space. Now the value which is either found or not found in that problem space, and we basically exit out of that problem space. Now, if we would not have identified the problem space itself, so then we would have gone into the else loop wherein we make the value of the start counter equal to end, and the end counter is basically the minimum of the start plus jump size and n minus 1. So it could well as be the case that okay, when we add that value jump size value to the start, it might be exceeding the end index. So we should not be exceeding the end index in any case, right? Because the element wherein we will be comparing that will not be existing and we will get an error. So we basically need to have the minimum value of these two, wherein the maximum value that the end element would have is n minus 1, and we return the found at the last. So now if we basically execute it and we execute some of the test cases. So for an example, the test case 1 wherein we have this particular list and we want to search for the element 1 in this sorted list 0 to 5. So that executes here. So we have 0, 1, 2, 3, 4, 5 as the list sorted list, and the value to be searched as 1. So we are doing first for the problem space search. So we have the problem space, first problem space as start with the coordinates of start as 0 and end as 2. So 0, 1, 2, this is our first problem space, and we have the jump size of 2. That is fine because um, the length of the array is 5, and we take under root of 5, that is 2.232. The integer of it is 2, and the current element we find out as the maximum or the end element of this problem space is 2, which is greater than the value that we need to search for, which is 1. So now we get into the linear search mode and we search linearly started from the end. So we have the current index as 2 and the current element is 2. So we come to the next iteration where the current index is 1 and current element is 1, which matches to 1, and hence we exit the loop. So this is how the implementation has been done, and this is available to you to have a look into the GitHub link, which is attached in this video description. Uh, I would suggest please have a I would suggest you to have a second look onto this particular algorithm and work it out on paper with a pen, and try to see if you are able to get that algorithm right. Try it a couple of times, give it a thought, exercise over it for a couple of times, and try to implement it without looking into the current implementation that has been provided. For any help, you can always put it in the comment, or you can always have a look at this particular GitHub implementation. So hopefully this was helpful for you to understand the jump search algorithm. Thank you.